Okay, so this is my first YouTube lecture, and in this lecture we are going to learn something about the probabilistic methods for graph problems. Okay, so as the name suggests, we will use probabilistic tools to solve some graph theoretical problems. Okay, so first let us define the term clique. So I am assuming that you are a little bit familiar with graph theory and what do we mean by graphs. Okay, so a clique is basically a set say S of the vertex set of the graph G such that the vertices of S are pairwise adjacent. Okay, and what do we mean by an independent set? Again, it is a set, say I, of vertices of the graph G such that the vertices of I are pairwise non-adjacent. Okay, so let me create an example over here. So suppose we are given a graph this. Okay, so these red one are the vertices over there. Okay, so now as you can see the definition of clique, it is a set of pairwise adjacent vertices. So basically when you are taking say these vertices, this vertex, and this vertex, so you can say let me write the names. So this is your v1, v2, v3, v4, v5. So you see the set S equals to v1, v2, v3. So you can see that v1 is adjacent to v2, v2 is adjacent to v3, v1 is adjacent to v3. So that's why this set S is a clique. Okay, now you see that a set I equals to this v4, this v2, and this v5. Okay, set v4, v2, and v5. You can see that v4 is non-adjacent to v2. We don't have any edge between v4 and v2, and similarly we don't have any edge between v2 to v5 and v4 to v5. Okay, so that's why I is an independent set over here. And similarly you can see that v1, v3, v4 is also a clique, and v5, v3 is an independent set. So that's why in a graph there may be several cliques and several independent sets, right? Okay, now let me define complete graph. Okay, so a graph on say n vertices consisting all possible edges. We will denote these by say kn. Okay, so what do we mean? K5 will be a graph on 5 vertices and all possible edges will be there. So you must know that all the things I will be talking here are about simple graphs only. Okay, So you can see that all possible edges are there. So this is a k5. Similarly, you can draw k4, k3, k6 and all that. Okay, so these are simple notations, but for the sake of completeness I am going through these. Now let me define a more technical term, Ramsey number. Okay, so what do we mean by Ramsey number? So there was a theorem which I'll be stating. So the theorem states like, for given positive integers, say k and l, there exists a positive integer n that obviously depends upon k and l, such that any graph on n vertices, on we can say at least n vertices, on at least n vertices contains a clique of size k or an independent set of size. So what does that means? Basically that means say you want to say k equals to 9 and l equals to 10. So basically depending upon this 9 and 10, there must be, this will imply there an existence of an integer n, which will be very large, maybe 10,000 or lakh, such that a graph, any graph on n vertices, okay, there exists some n, such that any graph on n vertices will either contain a, not either, that will contain a clique s of size 9. So it may have a clique of size 9, this has size 9, or an independent set of size, independent set of size 10. So this is what we mean by a Ramsey number, the theorem, that given integers k and l, we will definitely find an integer n such that any graph on n or more vertices will contain a clique of size k or an independent set of size l. Okay, so the Ramsey number is smallest such in. Ramsey number, we denote it by r depending on k, l, n, is smallest such n, right? So the smallest value of n will be the Ramsey number. So basically this theorem confirms the existence of such number n, and the minimum that will obviously exist will be the Ramsey number. Okay, so before moving to the probabilistic things, let me show you an equivalent definition of Ramsey numbers. Okay, an equivalent definition of Ramsey number is, say, r depending upon two positive integers k and l is the smallest positive integer n such that in any two coloring say with red and blue, any two coloring of the edges of the complete graph kn, so that in any two coloring of the edges of the complete graph kn, there is a red kk or a blue kl. So I will be illustrating this. What does this mean? Okay. So we can it's like you are given a complete graph, say k5. Let us say k5. Okay, we have a k5 over here, and we are just two coloring the edges of this k5. Two coloring means the coloring need not be proper. If you are knowing the definition of proper coloring, so it will be a bit ambiguous, but two coloring that need not be proper. You just randomly assign colors, either red or blue. Like I'm giving this blue, giving this blue, giving this blue, okay, giving this blue, and remaining others. Let me give this red, 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 this red, and this way red. Okay, right. So this is a two coloring of k5. Okay, and here you can see that say you see this vertex, and this vertex. So basically you see that there is a red k3. Okay, so we have a red k3 in this k5. But what about blue? We do not have a blue k3, but we have a blue k2. Okay, so you can see you just take this one and this one, so that will be a blue k2. Okay, so let us go to the definition again. This I was explaining the two coloring thing of a complete graph. Okay, so the definition says that you take kn, and you are randomly assigning two colorings to the edges of this graph, and you must be able to find either a red kk or a blue kk. Then the smallest such n will be the Ramsey number. Okay, and how this definition is equivalent to the previous definition that we learned. So basically you know that any graph on n vertices is a subgraph of a complete graph on n vertices, or you can say kn, right? So you simply in any two coloring you can simply in kn you just keep the red edges and remove the blue edges. In that way you can create G, right? So finding a clique of size k is equivalent to finding a red kk, and finding an independent set of size L is equivalent to finding a blue KL, right? So in that way the definitions are equivalent. Okay, so let me give you an example over here. So it is well known that R3 equals to 6. So what does that mean? It means in this new definition we can say that if you have a k6, okay, k6 over here, right? I think all the edges have been drawn. Okay, so this is your k6, and however you are assigning two colors to the edges of this k6, you will definitely find however to color the edges of k6, or you can say kn, n at least 6. Okay, however to color the edges of this kn, there exist a red k3 or a blue K3. Okay, so basically this result is very famous and it is known as the theorem of friends and strangers. I think it was okay, the theorem of friends and strangers. So you can see that this is stated as in a group of 6 peoples. Okay, there exist 3 complete friends or 3 complete strangers. Complete strangers means nobody is knowing nobody. So if you are collecting 6 people, either 3 people will be knowing each other, or there will be 3 people who won't be knowing each other. So at least one will be there. Okay, so this is famously known as the theorem of friends and strangers, and its value is 6. So basically that says R33 is 6. Okay, let us go to the main result of today's lecture. Okay, so it says, so and choose k 2 to the power 1 minus k choose 2 is less than 1, then rkk is greater than n. Okay, so this is our theorem that we are going to prove using the probabilistic tools. And how we are going to do that, so first let me tell you what this statement means. So we have 2 integers n and k which are related by this inequality. Okay, so if this inequality holds, then the Ramsey number rkk will be more than n. So that means this result will provide a lower bound for the Ramsey number rkk. Okay, so let me prove this thing. So first we are assuming this result, and choose k to the power 1 minus k choose 2 is less than 1. Okay, first we are assuming this, and now consider k. Okay, randomly color the edges of cane by red and blue. Okay, so we are considering a complete graph on n vertices, and we are just randomly assigning colors to the edges. So you just means toss a coin. If it is head, you give color red to the edge, and if it's tail, you give the color blue, and for each edge you will do, and that's how you can get a random 2 coloring of the edges of cane. Okay, now in this random 2 coloring we will search for a monochromatic kk. Okay, let S be a subset of B cane of size k. Okay, we have suppose this is your cane, and you are taking a set S whose size is at most this is small k, which is given in the statement, right? Now, so let AS be the event. I'm assuming that you know a little bit about probability. Let AS be the event that edge set on S is monochromatic, right? So basically all the edges in this S are just monochromatic, means either they are all red or they are all blue. Okay, so what is the probability of happening of this? So you you can easily tell that suppose all the edges in that S are colored red. So since each edge is getting half probability of getting red color, okay, since it is being colored with either red or blue, so half probability is there that it is colored with red color. And for each edge we have half probability, so by the rule of multiplication, okay, how many times, so how many edges are there in that set S? Since the set S has cardinality k, so the number of edges in S will be k choose 2, right? Okay, so but one thing is we are missing there, that we are considering that all the edges in S are colored red. So basically we can do the same thing when all the colors are blue. So this thing plus the same thing, so that means this will give you how much? So 1/2 to the power k choose 2, okay, into 2. So that will be how much? That will be 2 to the power 1 minus k choose 2, right? So that will be the value probability of happening of S, means the event that all the edges in S are monochromatic, right? So now the set S has cardinality k. So how can we how much such S can be there, such set S? So S has k element, so S can be made in n choose k ways, okay. S can be formed in n choose k ways, right? And in any of this S, in any of this S, if we are finding a monochromatic, then our job is done, monochromatic S, right? So what is the probability? Probability that a set of size k in Kn, small k, Kn is monochromatic. So basically this will be n choose k times this value 2 to the power 1 minus k choose 2. So I hope you all understood this. Okay, so now we are assuming, in the very beginning we are assuming that this value is less than 1. So this is strictly less than 1, okay. So what does that mean? That this implies probability that the complement of this, no set of size k in Kn is monochromatic. Since it is less than 1, so the probability of this will be greater than 0. So what does that means? That means that in our sample space there exists two coloring of the edges of Kn, so that we don't have a monochromatic set of size k, okay. We don't have a red kk or a blue kk, okay. So this implies there exists a two coloring of edges of Kn in the sample space such that there is no red kk and no blue kk. So definitely this implies the Ramsey number Rkk must be greater than this n, since in this Kn we cannot find a monochromatic kk, right? So that's how our theorem is proved over there. Fine. So I hope you all understood this. So now so this is a bit complicated to understand, the statement of theorem, but this theorem implies a very basic result, or we can create some conclusions over here. So we are taking this value n choose k 2 to the power 1 minus k choose 2 to be less than 1, right? So let us simplify these things. So n choose k means n minus 1 up to n minus k plus 1, right? And below we have k factorial, and this is 2 to the power 1 minus k minus 1 by 2. This is less than 1, okay? And this implies what? So n minus 1, n minus k plus 1, 2 to the power 1 minus k square by 2 plus k by 2, okay? This is less than 1, okay? And you know that we can the upper bound to this will be n to the power k, right? So that is we know n choose k 2 to the power 1 minus k choose 2 is less than n to the power k by k factorial, and 2 to the power 1 minus k square by 2 plus k by 2, okay? And now if you are taking n equals to floor of 2 to the power k by 2, so what will happen? We have n choose k 2 to the power 1 minus k choose 2 is less than this one will become how much? Floor of 2 to the power k by 2 to the power k, and 2 to the power 1 minus k square by 2 plus k by 2, whole thing divided by k factorial, and several things will can be cancelled, and it will bounded by how much? This will be just 2 to the power 1 plus k by 2, and here we have k factorial, and obviously this is very very small, less than 1 if k is at least 3, okay? You know that this value will be very small, right? So what does that means? That is, if n is equals to this 2 to the power k by 2, this then rkk is greater than or you can say rkk is greater than floor of 2 to the power k by 2, okay? So that simply means say r10 r20 so this will be greater than floor of 2 to the power how much? 10. So that will be 1024, right? So basically that means that in K1024, okay, there in K1024 there exists a two coloring of edges such that there is no red K20 and no blue K20. Means you cannot find 20 vertices whose incident edges are all red, or you cannot find any 20 vertices whose incident edges are all blue. So that's what it means. So one may ask a question that okay, we know that R2020 is greater than 1024 and there will exist a coloring, right? But how can we produce a coloring of that kind? So that's a good question. Okay, how can we find two coloring of the edges in which we cannot see a red 20 or a blue 20, right? So what I can suggest you that you just randomly assign colors to K1024 to produce such coloring, just randomly assign red or blue to the edges of K1024. Randomly means you can just toss a coin, and then if it is head, you assign color red. If it is blue, you assign color blue. So in that way, you just randomly assign colors to the edges of. And what is the probability of finding a monochromatic K20? Probability of finding a monochromatic K20 will be what we have counted over there. This will be how much? This will be this value. Okay, so 2 to the power 1 plus, what about k by 2? That is 10 by how much? This will be 20 factorial, k factorial, right? This will be less than this. Okay, and this value will be 2048 by 20 factorial. So you see the denominator is very large quantity, so this will be very, very smaller than 1, and you can say this is actually close to 0. So that means any random coloring may work. Means probability of finding a monochromatic K20 is near to 0. That means you assign randomly the color red and blue to the edges of K1024, and you can say that we can safely create a coloring in which we cannot find a red K20 and blue K20. Okay, so that's it for today. I hope you enjoyed it. Thank you.